Oh, continuing with chapter 4, starting with energy flux where we left off last time. So energy flux, represented by this Greek letter phi, is energy per area. And the area changes as the angle of the sunlight changes. So as our angle becomes greater, okay, as our angle becomes greater, the angle that we are measuring, um, so the angle from the horizontal, so well the angle from the vertical is becoming greater, but the angle from the horizontal, I'm reading this last sentence here. So the sunlight traveling through an area at an angle of theta from the horizontal is stretched out to an area. So the angle theta measured relative to the horizontal, which would be this right here. So it'd be this angle. This would be theta. So theta is getting smaller as the sunlight becomes less vertical, which would be less overhead sunlight. It would be the sunlight that you would associate with winter as theta became smaller, because winter sunlight is sunlight that's coming from closer to the horizon. And the sun never rises very high in the sky. Those are your winter months. Those are your months that correspond to whatever hemisphere you're in and the less sunlight in that hemisphere. All right. So December in the middle of winter, at least in the northern hemisphere, and the month of June in the southern hemisphere for their winter. So then theta is smaller. Going back to the equation, when theta is smaller, you're going to have this equation become or give you a larger area, because as theta becomes smaller, this formula here, the sine theta, becomes a bigger term, and then you're going to be dividing by a bigger number. And as you divide by a bigger number, well, if you take something where the numerator is constant, but you're dividing by a larger and larger denominator, you're going to get a smaller and smaller result. All right. So what you're getting is you're going to get, oh, well, actually, we don't want that though. I keep doing it backwards. Sorry. The third time I've done it backwards. So your area is going to get bigger and bigger. So because yeah, as theta becomes smaller, I'll write it out. So as theta becomes smaller, that's why it's important how theta is defined, because you could just as easily define it relative to the vertical. Sine theta, and I'm just going to tell you, you wouldn't have to solve this yourself, but then sine theta, just think about our sine function. Sine's zero when theta is zero, right? So then we're going to have something where it's decreasing as theta is decreasing. Yeah. So we have then that sine theta, thought about what the function looks like, is also going to decrease. So this down arrow just represents the trend. So as theta becomes smaller, which means as the sunlight becomes less overhead, sine theta also becomes smaller. As sine theta becomes smaller, since the area in the numerator is a constant, it cannot change in our explanation, because it's just, whatever, the light, whatever area the light's passing through in outer space, essentially. So it's like, because all the sunlight has to come from somewhere, and that's what a naught is. If you remember, a naught was initially defined kind of right here, and they showed it as like kind of this aperture, this opening that was above the surface. That's why I say it might as well be in outer space. It's just this, fixed amount of light from the source. All right. So that was the different angles. So a naught cannot change. It's meant to be a constant. So then finally we have that a decreasing value in the denominator, therefore the area is increasing. And that's what we want. And the reason we want the area to be increasing is actually because of the last step, which is it hopefully a good demonstration of how these ideas all tie together, is because if the area increases, well, look up here. Look at the formula. If the area goes up, well, the energy is a fixed value. Okay? The energy is the energy coming from the sun. The sun only produces so much energy. So if you have a greater area, but the same amount of energy, then you have less energy flux. So that's what's gone down. When the sunlight is less directly overhead, the flux goes down. Goes area goes up, flux goes down. And that makes the light less intense. And as I said, I would mention, intensity is really closely related to the energy flux. The only difference is that the numerator is power instead of energy. So all intensity is just saying, okay, well, we're just going to have it, over time, because power is energy per time. All right, but I won't get into that right now. We have other things to talk about, and we can see that in the homework. All right, so all of this discussion of energy flux was really within the same section of the slides on the sun angle, which was what we talked about when we introduced the rules for finding the angle of the sunlight at the solstice for different latitudes when we considered Eugene, Oregon as an example. So all of that and this discussion of energy flux are all related. So just to finish up that relationship, let's consider a point where the sunlight is coming directly overhead, right? So in this case, at this particular latitude, at this particular day, and the reason I know it's a particular day is look at the tilt, right? This is a day where the northern hemisphere is tilted towards the sun. And in this figure, we're seeing the sun as just the incoming sunlight. So, and based on the amount of tilt, it's probably the summer solstice, the northern hemisphere summer solstice. So maximum tilt, right? This is our 23 and a half degrees. Right? We're tilted all the way. The North Pole at least is tilted all the way towards the sun as much as it'll ever tilt. And we have some latitude right here where the sunlight is directly overhead. In other words, the direction of the sunlight and the zenith direction are parallel, they coincide. And that would create maximum energy flux because we would have minimum area for a fixed amount of energy. So this is the most intense sunlight, the most energy being delivered by the sunlight. All right, so let's check our understanding of this. I was trying not to give away the answer with my explanation. So looking at that, that particular case in that latitude, at what latitude is the sun right at the zenith on the summer solstice? What latitude would this be that would, match this picture where the sunlight is directly overhead?
Number 2,
All right, how do you know?
because it would be 23.5.
Yeah, okay. Yeah, because of the tilt, right? Yeah. Yep. You basically probably just use that formula that from the previous slide, right? Yeah. Does what's the significance of that latitude? Does it have a special name? Like, like kind of like the latitude that corresponds to the Arctic is called the Arctic Circle and the Antarctic Circle. Does this latitude have a special name? Anybody know? Either tell me with your microphone or put it in chat if you do know. Does 23.5 degrees north of the equator have a special name? Yeah, cool. Thank you. It wasn't something that you necessarily knew, but I just wanted to give you all a chance. It is the Tropic of Cancer. That's exactly it. And you could just said, one of the tropics, but that's it. And that's why we have the tropics. That's what they represent is a a latitude where the sun is directly overhead by one day out of the year. All right. Very good. 23.5 degrees. All right. So just fix that and we'll carry on. Tropic of Cancer. Okay. So there's the Tropic of Cancer. The sun is at the zenith at noon on the summer, which is the June solstice. And here, the reason that they're clarifying that it's June is because, summer is a kind of a vague term, right? We saw that summer means something different in the southern hemisphere. So we could, to be more exact, we could just call it the June solstice. All right. Here is that formula that I referenced just a second ago. We saw this on Thursday when we were talking about finding the angle at other latitudes. Okay. So this is how you find the sun's altitude. In this case, you can see right away you'd have axial tilt minus latitude. And if it seems slightly different, it's because last time we saw the formula, it was written in a different order. But of course, the order of subtraction and addition, you know, doesn't matter. So, whether it's minus latitude or plus axis, doesn't matter. But anyway, so you'd have the 23.5 degrees right here, and then you subtract, well, these would just cancel. So, 23.5 minus 23.5 is just going to give you 90. Hopefully that's legible. There you go. All right. Then we could do the same in the southern hemisphere. We haven't talked too much about the rules of sun's altitude at particular dates in the south, although I said that very similar rules. You just have to take into account that latitudes are defined as negative. Okay, but here we have the Tropic of Cancer. This is the sun at the zenith. Zenith, again, being directly overhead at noon on the winter December solstice. All right. So these are the tropics. Everything between these two latitudes has one day of the year where the sun is directly overhead. All right. And as a very, it's not something you're responsible for, that it actually is. It's just one day of the year for each point, except for because of a combination of the elliptical nature of our orbit combined with the tilt. There's actually one latitude, 9 degrees north, where they have 2 days out of the year where the sun is directly overhead. And that whole idea is related to something called the analemma, which is the apparent path of the sun to the sky, but not something that we cover in the textbook. So ignore it. But if it sounds kind of interesting, it's a cool idea. All right. So going back briefly to discuss the equinox, this is the point where the angle of the sun from the zenith is the same at all latitudes. So it does not vary. The equa here is relating to the equals. Right, that's the idea. They underline the word equals to remind you that equinox and equals have the same root, the same, etymology of the word. So at the equinox, is the energy flux of sunlight larger in Eugene or in La Paz? Hopefully it's a easy question. At the equinox, either one, either the spring or fall equinox, is the energy flux of sunlight larger in Eugene or in La Paz? All right, so people had some time to think about it. All right. Yeah, I guess the more I thought about it, the less easy it seemed to me. So I can see I can, yeah, I understand the question mark, not being totally confident about it. First, I was like, oh, this is totally easy. Then it's like, oh, maybe not so much. So just to go back here, so they get the angle of the sun from the zenith, all right, equals the latitude. So what I think there's a phrase that I said that I think was misleading. So I want to hopefully clarify it. I'm like, oh, well, it's that. So it's like, the same everywhere. Well, it's the same relationship everywhere, but it's still going to depend on your latitude. Yeah, so it's still going to depend on your latitude. It's the what is absolutely shared, by the way, at the both the equinoxes is the length of the day. So at the equinox, every single latitude on Earth has a 12-hour day and a 12-hour night. So that is just universal. But what it means to have a 12-hour day and a 12-hour night is not universal across every single latitude. I mean, if you think about the very North Pole at, the spring equinox, sure, they have 12 hours of light and 12 hours of darkness, but the light and the darkness are like the sun would just be like right at the horizon. So it's going to be it might as well, not really be 12 hours of light and dark. And if you go just a little bit south of the North Pole, then you'd have, 12 hours of the sun just a little bit above the horizon, and then 12 hours of the sun just a little bit below the horizon, which would really be like a twilight. So that's what their day and night would be like. Very different from the day and night in the tropics. So yeah, with that consideration and with this statement, the angle of the sun equals the latitude at the equinox, then we can come up with the following result that it is in fact La Paz, because La Paz has the smaller latitude in terms of its value. Okay, therefore it's going to have sunlight where it's closer to the vertical. It's just simply closer to the vertical. All right, so it's going to be more directly overhead. Not quite, directly overhead, but pretty close to it. All right, so that gives us the following formula. So we have this following formula to relate to simply find the altitude of the sun. Okay, and just like before, the formula that we had only applied to the summer solstice. This one only applies to the equinox. So we have these formulas for finding the altitude at particular days. And yeah, could you come up with a formula to find the altitude every day of the year? Sure. But it'd be complicated because you have to consider, what those, what it means to have a circle, how that relates in a complicated geometric way. So what we're focused on are just these straight line special days where we're not worrying about the elliptical orbit. We're just considering special cases. All right. And yeah, and they apply to noon because obviously the sun takes different altitudes at different points. So whenever we talk about the sun's altitude, we're talking either about its maximum altitude or specifically at its altitude at noon. And here, in really, we couldn't say that for other days of the year for the winter solstice because noon's not necessarily going to be the middle of the day, but at the equinox it is. So you can safely say that it corresponds to a time of noon. But it's almost not necessary. I think it's better just to say maximum altitude. All right. So then to kind of summarize and compare this new formula for finding the altitude. We got, the one for the equinox. We have the one we saw before that we saw last Thursday for the summer solstice. Okay. Quick reminder that the summer solstice corresponds to June in the northern hemisphere, coming up in a few days. for us in the northern hemisphere, and then corresponds to December in the southern hemisphere. So which is what we call the winter, well, our winter, right? December 20th. Okay. And then the formula for the winter solstice, all right? Let me use the same formula here. Okay. Let's take a quick look. Could we use it for if we wanted to find, so if we plugged in a negative, yeah, so the winter solstice we're subtracting. And if we wanted to use this for our latitude to find the altitude, I'm thinking about if we wanted to use say like the winter solstice formula for the southern hemisphere. Well, if I plugged in a latitude right here, but I plugged in a negative value, then it would not work. So if you I bring that up because when we saw the slides before and we saw these rules for the solstices, then they the slides were kind of careful to only point out that the formula is applied to the northern hemisphere. Now you're seeing a summary that includes some mention of the southern hemisphere as well. And I can see why, because hey, we just saw a rule that applies to both, the rule for the equinox. Okay, so we got 3 special days of the year, 2 hemispheres to consider. But here's my warning to you, is that yes, you can absolutely use the formula for both hemispheres, but when you do, and you consider that in the southern hemisphere, this rule for summer would apply to days in December. That's your first consideration. But the more important one is to remember that you want to use the absolute value of the latitude. So you have to drop the negative. You can't use the negative latitude. So if you're at, 16.5 degrees south, like La Paz, you would have to use just 16.5. You might think, oh, it's you'd be thorough and being careful to use the negative because technically southern latitudes are negative. But if you did, you would get the wrong result. So this formula as written will work for both hemispheres, but you have to take the absolute value. So it's always the absolute value, which you can just remember is just drop the negative. Absolute value, which is better than having two separate formulas in a sense. It's easier just to remember that you just every time you take your latitude, you don't care. You just plug it in as a number greater than 0. Okay, so hopefully that's clear. And we'll carry on. Quick example, look at the equator, summer solstice. All right. So they have a location in Kenya, basically at the equator, right? Just 1/10 of a degree off. Okay. Then looking at that same latitude, again, basically equatorial at the equinox. So we went from the sun being not quite at the vertical in December. Okay. And then we had it right vertical at the equinox. And then in the winter, here it is, the equal number of degrees off, but the other way, right? So at this equatorial location, there's not a lot of change, right? Which is why there's not well-defined seasonal differences for equatorial latitudes. The sun is always pretty close to directly overhead. It's only going to take a full, 40, 47-degree arc across the sky, which keeps it in very much the directly overhead position. Okay. If you look at a high northern latitude, look at the summer where this is, and notice this is in Moscow, right? So 55.75 degrees north, below the Arctic Circle, but still quite far north. Our summer solstice, this is where the sun is as high as possible as it's going to get, the largest altitude it has. And it's not even as high right? As the sun was when it was as low as it was going to be at the equator. If we go to the equinox, the sun is even lower in the sky. And if we go to the winter solstice, this is the sun's maximum altitude at the winter solstice. So, the sun rose, moved up to the sky, took an arc across the sky as it moved from east to west, but that arc, it never went very high. So it would have stayed towards the south. So if you look toward, it says from in the northern hemisphere, that arc is always going to be in the southern direction. If you're in the southern hemisphere at a altitude, or rather a latitude that's kind of, close to the Antarctic, then you're going to see the sun take a path towards your north direction, but it will always still, rise in the east and set in the west. But despite that, its highest altitude would be not very high, right? Which is why it's just not enough sunlight to actually warm the surface, you know, keeps everything cold. All right. So that finally wraps up the whole idea about the axial tilt and why we have those seasonal variations, what it means to have energy flux, less intense sunlight. Okay. One thing that I always find so curious, and I've never really actually gotten a good answer to this, is that in not the answer to the concept, but answer to more like the way that the subject is taught, um, is that notice that we really just talked about the the idea of energy flux. Everything we focused on was about how the sunlight gets spread out and the altitude of the sun is, varies at different latitudes, which is great and is, you know, de deserves attention. But there's also the length of the day, and the two factors contribute to each other. And I think it's maybe because the length of the day is considered sort of trivial compared to the whole explanation that we just went into, that it doesn't get the attention that it deserves. But it's worth considering those two things combined. Not only is the sun not reaching a very high altitude in the local sky, but the day is shorter as well. So, remember that there's both those factors. You have less intense sunlight, less energy flux, and you also have less time for that energy to do anything. Okay, but now really done with the sunlight discussion. Let's move on to something that might seem like a big adjustment, a big change, but still a lot of the same ideas in terms of thinking about relative motion. Before we were focused on the tilt of the planet and our planet and how that tilt remains fixed throughout our orbit around the sun. And everything else followed from that basic idea. We are always tilted in one way relative to the distant stars, and our tilt is not relative to the sun. Okay, well, now let's think about another argument, the motion of the moon. The moon moves around Earth, not around the sun. Okay. And the orbit of the moon around Earth is independent of the orbit of the Earth around the sun. So that's kind of, the same sort of idea, is that we're going to have different orientations of the moon relative to the Earth and the sun. One thing that initially we won't have to consider is both the orbit of the moon around the Earth combined with the orbit of the Earth around the sun. We'll only have to consider that combination of motion when we talk about eclipses. For now, we can imagine the sun as just being fixed in place. And that's what this kind of incoming sunlight is going to represent. What I mean by that is that it doesn't matter if we're at perihelion or aphelion. It doesn't matter if we're at the equinox. This little diagram here could represent any one full orbit of the moon around Earth at any point in the year. All we care about is that the sun is somewhere off to the side, in this case, the right side, and the sunlight's coming in. Okay? So consider that for now. As we clearly look at these different points of the moon going around Earth, we can see right away that they're are identified by letters A, B, C, D, E, F, G, H. The order of the letters show us that our perspective here is showing the moon in its counterclockwise orbit. And remember, that's the direction that everything goes. Every motion in the solar system is counterclockwise with a few exceptions. But those exceptions are so important that they're called retrograde motion. And there's only a couple of them. Otherwise, everything spins and orbits in the counterclockwise direction, which is called the prograde direction. So it's the dominant direction of the solar system and the dominant direction of the galaxy. No coincidence. All right, so we have that motion of the moon around Earth. One of the phases is labeled just one though, the new phase. This would be the phase of the moon that restarts the cycle. And then let's look at our other phases. Okay, so starting with a new moon, the next phase, we're just going to go through the names, make sure we get these out of the way. So our next phase of the moon is called a waxing crescent. So we go from a new moon to a moon that's just, barely anything. So it's growing. Waxing refers to growing. Crescent obviously refers to the part that's illuminated. Okay. And if you're wondering about the difference between the pictures, I'll mention that in just a second, because this waxing crescent corresponds to figure B and also, this figure. So, how can it be both? Okay. All right. Well, then I'll get back to that. Then we get to the first quarter. Now, is there something between the waxing crescent and the first quarter? Sure, a few days, but there's no special name for it. The actual named phases are just the ones showing. So the first quarter, all right, and that corresponds to point C. Then, after the moon goes through its first quarter phase, then it reaches what's called a gibbous phase. And we have a waxing gibbous because this is the growing gibbous. Gibbous means that it's more than half illuminated from what we can see. Because notice the first quarter phase, from the perspective, and this is kind of touching on the different views, but from the perspective of a viewer, so in your local sky, would appear as half illuminated. So a crescent, less than half illuminated, as seen in the sky, gibbous, more than half illuminated. Then we got a full moon. Okay. Full moon, full circle. Okay. That's what one day, one night in the cycle. After that, well, now the moon starts to shrink. So once it becomes full, it has to return to being a new moon. So as we move on to point F, we have a waning gibbous. Waning just means shrinking. Then, no surprise, third quarter. Okay, so that's what the third quarter moon would look like in the sky, as shown right here. After the third quarter, it continues to shrink as it approaches that new moon phase, and it becomes a waning crescent. Okay, so perspectives. Okay, so all the lettered phases of the moon shown in orbit around the Earth in that counterclockwise direction are as they would look from a observer that is some distance above the ecliptic plane looking down onto Earth. So if you were an alien in a spaceship or just a space traveler and you look down on the Earth, not at all to scale, right? Because the moon is way too big and too close, right? Especially too close. Then this is what the moon would look like. We'd always see that half of it is illuminated because it is. It's always half illuminated. Okay? So half of the moon is always illuminated. The other half is always in shadow. And we just see it at different orientations relative to the Earth. But of course, when you're on Earth, what you would see is different. What you would see are the phases, because now your view isn't that of an observer above the orbit, but instead at the center of the orbit of the moon. So now, when you look at point A, for example, you can't see the half that is illuminated. So from your perspective, it just looks like a dark disk. It's almost too dim to see because there would be, there's no reflected light that's reflecting off the moon's surface and making it to your eyes. So if you're right here, an observer on the surface of the Earth, and you're looking at the moon, you can't see this shiny side because the moon is very shiny. That's all we're seeing is the reflected light. It's like, it has what's called a high albedo. It's a very, very reflective material, the dust that covers the moon. In most planet surfaces are fairly reflective, some aren't. If the whole Earth was covered in something that kind of had the color of coal, then it wouldn't be that reflective. But this is more like a bright sand on the moon called the regolith. And so, because of its reflective nature, when it's at an orientation where the sunlight's bouncing off it and making its way to your eyes, then you can really clearly see the moon. And of course, that's what happens at a full moon. So, at a full moon, at an observer located right here, during the night on Earth, they look up and they see a fully illuminated moon because they're seeing all the sunlight reflected off the moon, making its way back to their eyes. And that gets me to the last point and the last labels in this figure, which are the times of day. So dawn, dusk for the new moon, noon, midnight for the first quarter, dusk, dawn. You think of this dusk till dawn, midnight to noon for the third quarter, and then back to dawn to dusk for the noon. And so what does that mean? Well, that's when it's visible. And you can just look at these and sort of just memorize them and sort of reason it out. But you also just look at the Earth here. So this is the Earth. You can see what side of the planet has day, what side has night. Okay? Well, at a moment in time where the day side of the Earth has the moon between it and the sun, that corresponds to the phase known as the new moon. Because, in other words, you can only see a new moon during the day, which is all the more reason of why you can't really see a new moon. Not only is it not reflecting any sunlight, but it rises and sets with at approximately the same time that the sun rises and sets. So it's completely obscured by the brightness of the sun. It's not like, overlaying with the sun, not in most cases at least, but it's just, completely washed out. Okay. So, and the reason it has to rise and set with the sun is because of this relative orientation. And each of these phases doesn't change much over the duration of a full day because it's important to remember the time frame here. The Earth takes 24 hours to make a full circle. So everyone on Earth is going to see the new moon in its, or not see it, but see this phase of the moon. Because by the time the moon gets to the next phase, or even between the new moon and the waxing gibbous, well, that's already been a day. And what I mean by that is the full time for the moon to go through this cycle from new back to new is 27 and a half days. So you've got, a full day per phase easily. So that's why you can always think that the phase is not going to change over the duration of a day is always a safe assumption. If you're trying to be really exact, yes, there is some sort of fractional change, but not enough to notice with the naked eye or for us to care about. All right, I think that's a good introduction I wanted to say. So we can move on. Just checked for any questions in chat. Looks good. Let me know if you have any questions at this point. All right. Okay, so slightly different perspective, summarizing same information. So here we're looking at the Earth. It's going around the sun. It's a 12th of Earth's orbit around the sun to complete a phase of the moon. So the Earth has moved a significant amount, but only enough to affect the difference between what we call a month, which we might touch on later. But here, this is our new moon phase to start things out, and then we return to a new moon phase over here. Okay, so again, moon as seen from above the orbital plane, above the ecliptic plane, and then down below, the moon is seen from Earth. Okay, so let's check your understanding. If you see a gibbous moon at 5 p.m., is it waxing or waning? Which one? Let's think about it myself without looking at the figure. I have it. Okay. So 5 p.m. Right. Yep. All right. So we got one vote in. Get a few other people. Okay. Cool. You all seem to get it. Waxing is correct. It is waxing. Can anyone explain how they got their answer? How do you know? Okay. Uh, because it's growing. But how do you know it's not a waning gibbous? In other words, because the moon is still phasing around 5. Okay. Because yeah, maybe you're probably thinking of the right way. It's just difficult to know how to explain it. I'll ask a leading question. Would you be able to see a waning gibbous at 5 p.m.? Is a waning gibbous visible at 5 p.m.? I definitely agree. The peak hours are midnight and noon. Yeah. So if it's a waxing gibbous, it's going to be, yep, I agree, going to be kind of visible during those hours. But can someone answer this question? Can you see a waning gibbous? I'll put it in chat too. Can you see a waning gibbous moon at 5 p.m.? Oh, I just realized I spelled waning wrong. No, that is a word though. I wonder. I'll have to look into that. But can you see a waning gibbous at 5 p.m.? Just yes or no. Okay. So, all right. So no, no, possibly no. All right. Okay. So let's think about it. We have the yeah. Okay. I have to now. I have to, I was my initial answer was definitely no. But then I want to make sure that I'm thinking about the right way. So if we think of a a first quarter moon, the first quarter moon I mean, these are just kind of approximations, but rises at noon. They're rounding, right? But they're pretty accurate. Rises at noon, sets at midnight. That's the first quarter, right? The full moon rises at sunset, which let's say it's easy to say it's like six. Okay, sure. I'll go back to it. Okay. So this one, and so what's really great is you can like approximate them. So this one, dusk till dawn, you can think of this one as 6 to 6. So 6 p.m. to 6 a.m., which obviously isn't always sunrise and sunset, but all you have to do is just say, hey, let's just do this at the equinox. Make it easy. And that's the way that I will always ask it of you if I ask these kind of questions. So, on an ideal equinox day, dusk is at 6 p.m., dawn is at 6 a.m. Great. So that's the full moon. Rises at 6 p.m., sets at 6 a.m. So there you go. Once we get to the waning gibbous, yeah, it is not visible at 5 p.m. because the waning gibbous would rise at around 9 p.m. because it has to rise later than the full, and it's going to set at around 9 a.m. So that, yeah, so good. I was totally confident. I almost second guessed myself, but absolutely. So a wait, which is actually necessary because otherwise that question would have been unanswerable, you know, not like confidently at least, or not with full, you know, you couldn't be sure that that was the right answer. But that's the idea is that if you see a waxing gibbous at 5 p.m., right, which is, before this time, it can't be, if you see a gibbous rather, it can't be waning. No, there's no in-class quiz today. We're doing it on Canvas. And then I'm just going to put down time for the waxing gibbous, so it's not like a point of confusion. Let's do so. This one here is going to be so it's earlier. So this would be around 3. So this one for the waxing gibbous, it rises around 3 p.m. and then it's going to set at around 3 a.m. And then the first quarter, it rises at noon and sets at midnight, which is 12 noon. I know confusingly is 12 p.m. and then midnight is 12 a.m. So you can just call them noon and midnight. But there you go. Homework is due tomorrow, homework 2. We're posting homework 3 soon. So I'm just responding to some questions in chat if you want to run jumping around. All right. And we're approaching our break, our mid-class break. So let's say a couple more words about phases of the moon first. Exactly. Exactly. Exactly, Alexander. It's about a 3-hour offset between the named phases. That's exactly right. And so if you look at it, you go so you got 3, 6, 9, 12. See? I'm kind of counting, right? So to go from new to full, that's 12 hours. So there you go. 24 hours to go all around. Yeah. Yeah. So the way that Alexander paraphrased it and summarized it is, I think, a great way to think about it. Remember that rule. Each phase has a 3-hour offset. All right. So continuing on. Let's hide this. There we go. All right. So waxy gibbous. So phases of the moon or phases of the pumpkin. Okay. So here we go. Here we got our light, right? The light is the sunlight coming from space. We move a pumpkin in a circle, All right, whoops, wrong way. You stand in front of the pumpkin. Maybe you're holding the pumpkin in your arms, and you hold it in front of yourself, and you see that all you see is the shadowed side of the pumpkin, and you turn your arms without turning your body. So you might want someone else to hold the pumpkin, and you could reenact this yourself. See? You could create the phases. You could also do it with a ball, and you can simulate the phases. You go in a dark room, go out at night, and you have like a single light source, like a flashlight, and you can simulate the phases of the moon, where your head represents Earth. And you just have to like, in this case, yeah, I guess you could actually turn your whole body and just hold your arms out straight, because then you're gonna sort of see the illumination. Because once you turn it all the way around and make sure your head's not shadowing things, then you'll see the fully illuminated pumpkin when you're facing away from the light. All right, so another quick concept question before our break. During a new moon, what percent of the moon's entire surface is illuminated by the sun? And notice that they put in parentheses, irrespective of what we see, which is always true. Every phase that we see is irrespective of what is illuminated, which is just a reminder because I mentioned that before, but also a hint. Okay, I got some answers. Hey, nice. You knew right what to say. 50%. Exactly, because it never changes. This question could mention any phase. It could say during a first quarter, during a third quarter, and the answer would always be the same, which is 350%. That's right. Very good. Okay. Arrow's kind of cut off, but 50%. That's how much of the moon is illuminated every single time. So that kind of gets into the idea of, you know, like, what does it mean by the dark side of the moon? There's no such thing, you know? Every side of the moon gets illuminated. There's no side of the moon that doesn't get sunlight, which, maybe you've already picked up on, maybe you already knew, but if not, yeah, you should be thinking about that now. But another question for you real fast, make sure that that idea and all these ideas make sense. During a new moon, what percentage of the moon's surface reflects sunlight in our direction? Because we just established that 50% of the moon is illuminated during a new moon, but how much of that light makes its way back to us? Hopefully an easy question. Yep, that's right. Zero. Oh, and real fast to answer Chase's question, there is no in-class quiz today. It's going to be on Canvas. There you go. 0%. None of it makes its way back. Cool. All right. So we'll go ahead and no problem. We'll have this be our break for now. And pause the recording, take a 5-minute break. We still got a couple slides on the moon, but I don't want to push it. We'll go ahead and just still take our break. Cool. And then cool. And then we'll just go right on to talking about eclipses. And yeah, I just want to see if we realistically can get through it. Definitely, especially because we have a bunch of concept questions at the end, which we don't have to go through all of them. Cool. All right, so we are on track to finish chapter 4 today. Let's go ahead and take a 5-minute break and come back together as a class at 11:22. Okay, so just continuing with lecture 4 and chapter 4. All right. So let's go ahead and resume the slideshow. Hide the floating meeting controls. Okay, so we had our 0%. Now, this figure that was included with both of the recent concept questions also showed up for the first time over here, and I want to briefly mention it because we're going to get back to this idea when we talk about the length of the day. But I hinted at the idea that since the moon takes a month, to be sort of vague about it, but takes a month to complete a full set of phases, that's a significant portion of the full orbit of the Earth around the sun. Because, of course, 12 months in a year, 12 lunar orbits. That means that the Earth has moved quite a bit by the time the moon returns to the same phase. So that means that the idea of returning to the same phase has to account for the Earth's orbit around the sun. Because if we only cared about the moon orbiting Earth, irregardless of the sun, we would have a shorter period. And those two periods of the lunar cycle have different names. We have the synodic lunar period, which is 27 and a half days, and that's for the moon to orbit the Earth, to completely orbit the Earth. And if you look, completely orbiting the Earth, you can actually see really clearly where it is in this figure, and because it's actually a nice feature of this figure. Notice the continents, right? So for the moon to completely orbit the Earth, it has to get back to the same exact position. And notice that it does that right here. See, like where the moon is relative to North America at, let's draw a quick arrow at this point right here, and then right here, it's at the same point. So that is a complete lunar orbit. And orbit would be the right word because the moon has gone all the way around the Earth, but it hasn't completed a set of phases. It has to go a little bit further to complete a set of phases. So the complete set of phases doesn't end until here, which is at 29 point, I think 2 or 29.3 days. So it takes almost two more Earth days for the moon to complete a set of phases than it does for it to complete an orbit. And that's because phases are dependent on sunlight. So if the Earth has moved a little bit in its orbit around the sun, getting the moon back to the same position in order to have the same amount of illumination takes a greater amount of time because it takes more than a full turn. And you can see here, it takes this much more of a full turn. And that's the difference between the synodic, which is the shorter of the two, and the solar month. And we mostly care about the solar month. The synodic month is only really the concern of people who study the moon and scientists and certain considerations, but mostly we care about the phases, so the solar month. And the solar month's the longer of the two. Okay. All right, so here are our concept questions. Okay. So we're looking at our mostly horizontal orbit of the moon. Okay. So what if the moon were vertical, however? What if the moon orbited across our poles? How would that change our perspective? Well, imagine that you're standing right at the North Pole, and each night for a month, you went outside to look up in the sky at the moon. Well, what would you see? Do you still see phases for the moon during that month? If so, how would they be different from how they are now? Right? So just an interesting thought experiment. So think about what your perspective would be. Of course, at the North Pole, like how would what would it look like? Probably the biggest thing, just to spoil some part of it for you, mostly I just want to leave this as an open question, is that the rising and setting makes that because the way the moon would rise and set or not rise and set would be the biggest difference? All right. This is that, again, the vertical moving pumpkin. So you could simulate this yourself, by imagining, make your head the earth, kind of spin around. What would you see? Right? This is hinting at the fact that you would see some sort of phases. They would be different, and they definitely would behave different relative to your local sky. Okay, so all of this segues nicely into talking about eclipses. We'll get back a little bit to that idea of the solar month and the synodic month at the very end of this chapter's lecture, the very last slides. However, we'll barely talk about the month. So, just to put that in the back of your mind. But I wanted to introduce it because we'll talk about the difference between the day, because just as there is a solar month and a non-solar month called the synodic, there's also a solar day and a non-solar day for the same exact reason. But before we get to that, let's talk about eclipses. So, still considering the phases of the moon, which phase produces a solar eclipse? Who can tell me? Which of the named phases produces a solar eclipse? Okay, see something in chat. New moon. Yeah, very good. Yep, so only a new moon can create a solar eclipse. Other phases would not be in the correct relative orientation to do it. Okay, so on a solar eclipse, we have the new moon basically entirely invisible. It's not, it doesn't reflect light. It, if you could see the new moon somehow without the sun, it would be like dim, but somewhat, because it still reflects, the light that is reflected off of Earth. So there's still some illumination. And also there's usually like kind of a bit of a perimeter light that's sort of like that's not that the moon has an atmosphere, but just because of some of the refraction of light that's happening, and on the very edges, there's some you'd be able to see something. But the fact that it's up during the day, it's totally invisible. It's just washed out. So you have no idea it's there, especially when it gets really near the sun. And then on certain days, you have the moon pass directly in between Earth and the sun. But this requires very specific conditions, which is why they don't happen all the time. Why, in other words, why every new moon is not a solar eclipse, because they're not. Only some new moons are solar eclipses. And on top of that, only some locations on Earth will be able to see the full solar eclipse. Very, very small portion of Earth called the path of totality. But this is the basic condition. And the reason it even happens at all is because of the unlikely coincidence, just very, very just like total happenstance that currently the moon and the sun have the same angular size in Earth's sky. Not exact, but within a percentage of a degree, they're the same size. The moon does vary enough because of its slightly elliptical orbit that sometimes the moon is a little too small if the solar eclipse happens to coincide with when the moon is at its apogee, which is kind of like our aphelion when it's furthest from Earth. And then you have what's called an annular solar eclipse, or sometimes called the ring of fire, because it doesn't completely cover the sun, and so it never really gets very dim. and you're not able to see the sun's corona. So they're not considered as dramatic, but they are fascinating and technically more rare. But in the future, and by the future I mean 60 million years from now, the moon will be further from Earth because it is moving away at a steady rate, due to the loss of energy from tidal friction between us and the moon. And then we'll never have total solar eclipses again. So at some point in the, about the same time that we in the future as we are from the extinction of the dinosaurs, there will no longer be solar eclipses. The Earth will definitely still be here. Sun will still be here. It's, in terms of geological and astronomical time, it's the near future, but not in terms of biological time, certainly. But regardless, then that will be the end of total solar eclipses. So it just happens to be something that happens now. This is showing the orientation that would lead to a solar eclipse. All right. This is just a new moon, right? Moon is just between Earth and the sun. Nothing is to scale here. Um, but what is new about this figure is that notice that we can see the shadow created by the moon is represented as a cone. That's the way shadows work. This is called the the umbra is the true shadow of the moon. Outside of the true shadow is the penumbra, which is the partial shadow, and that's where you get a partial solar eclipse, where you can notice that some of the sun is covered, the lighting is different, and maybe you've experienced some of those yourself. There, it's not like it doesn't become dark for 6 minutes in the middle of the day, like a when you're in the path of totality, but it's still pretty interesting. But then if you look at this, where that totality is that I keep mentioning, well, that's that little point right there that hits the surface of the Earth, and it's called the eclipse path. And so what happens is because of the moon's distance and what it means to have the same angular size, well, that closeness between the angular sizes of due to the actual size of the moon and its distance and the actual size of the sun and its distance, because that's how you find angular size. Well, if you if because again they're both about 5 degrees, or sorry, 0.5 degrees, or half a degree. Well, once you get down to the very end of that shadow, you have not like a single point, but something that's really narrow. So the actual size of the shadow of the moon is only about 50 miles across, or so that's 70 kilometers, as a kind of as a typical average for a total solar eclipse. That's the size of the shadow. And then that shadow, sweeps across either ocean, and not many people see it, which happens a lot of the time, or, sweeps across a continent or something, Dana Islands, whatever. And then if you're in that path of the shadow, that's only 70 kilometers wide, then you're able to see a total solar eclipse. And the actual event lasts somewhere between 4 and 7 minutes. And that's depending on where you are and based on the curvature. Because you can think about how that shadow is going to race across the earth, and it's going to race across the earth at the relative speed of the moon to the planet, which happens to be almost exactly 1,000 kilometers per second. All right, sorry, thousand meters per second, 1 kilometer per second. So that's the relative speed of the moon. It's its orbital speed to the Earth. So then the shadow moves across the surface at a speed of 1 kilometer per second. Well, because of its width, that's like that. That's how long you can be in that point, that shadow. But the shadow, just like how we talked about the intensity of light and how it gets stretched out, right? And that's how we have less intense sunlight at certain times of the year. Well, same thing here. The Except instead of it being a less intense solar eclipse, it's a longer one. So if you're like kind of on the edges of the curved surface where that shadow is racing across the planet, you can get a longer total solar eclipse. And that's why they can be as long as like 7 minutes, but as short as just a little bit under four. Okay. Lots of cool details. They're really, really fascinating. All right. And this is so see this. Do you see that big black spot? That's the shadow of the moon during a total solar eclipse as seen from the International Space Station. That's how big the shadow actually is. And it might look pretty big, but that's only about 70 kilometers wide and a little bit wider because they're seeing it reflected off the upper atmosphere. But that's not a big difference. The atmosphere itself is, very thin compared to the size of the Earth. Only about 100 kilometers as compared to, six thousand, for the radius. But there we have the shadow of the moon. So the moon is, really a great distance away, right? So the moon is like way, way up here. In fact, the moon is 60 times further from the surface of the Earth than we are from the center of the Earth. So, often when we show the moon, we think it's much closer than it is, but it's 60 times further from the Earth than the Earth's own radius. So it's way far away, but this is the shadow it's creating, okay, during a total solar eclipse. So there's only, in order for a solar eclipse to happen, okay, Earth has to pass through the moon's shadow. But I said that doesn't happen with every new moon. Well, why not? Okay? Because most of the time we miss it. And the reason we miss it is because of the small tilt of the moon's orbit relative to our orbit around the sun. And it's small. Okay, so here this would be a direct hit. But just the fact that it's there is enough. Okay? So the tilt of the moon's orbit is 5 degrees tilted relative to the ecliptic plane. I've used that term a lot, ecliptic plane. It's just the term for the plane created by our orbit around the sun. So there's moon's orbit 5 degrees off from our orbit around the sun. That's, of course, the moon's orbit around us, Earth. And what that looks like as a figure, I have another set of slides that I'll use to show it, is the following. One quick second. Well, different textbook. Okay, there we go. Okay, so here it is. The moon's orbit is tilted 5 degrees to the ecliptic plane. That means we have about 2 eclipse seasons each year. Okay, so there's 2 times each year where there is the potential for a solar eclipse and a lunar eclipse. All right. So, and they almost always happen. So there's about 2 solar eclipses every year. But the reason that you personally don't experience one is because they tend to pass over parts of the earth where you don't live, right? And sometimes they even don't happen because of, I was talking about sometimes it's an annular eclipse, right? But to visualize that, here we have the tilted lunar orbit around Earth, which is shown as the arrows. And this is the moon orbiting Earth. The ecliptic plane, for the purpose of illustrating this idea, is represented as the surface of a body of water, which I know is kind of fanciful, but it does a good job, right? And I'll show you why. Because we've got Earth's orbit around the sun, which is exactly on the surface of this imaginary, lake, this solar system size lake. The sun is kind of, half sunk down, or it's floating, right in the water. And so again, Earth is exactly on the water by definition, but the lunar orbit is tilted. So that means that the lunar orbit is sometimes beneath the surface, sometimes above. Well, if you have a new moon like this one right here, where you have a new moon above the ecliptic plane, that means there's no chance of an eclipse. There's zero chance of an eclipse happening when the new moon is tilted as shown right here. So you have to have these points where the moon is passing through a node, and the node is where the moon's orbit crosses the ecliptic plane. It's just the intersection of those two orbital planes, the orbital plane of the lunar orbit and the orbital plane of Earth's orbit. And when they intersect, that's where you have a chance of having an eclipse. That means you have to have a new moon coincide with that node. So you can see sometimes it doesn't happen, right? So sometimes, you the Earth passes through this point where there's a potential for the moon to coincide with a node, but the right phase never occurs while the node passes by. And so that would be a missed opportunity for a solar eclipse. So even though there's potentially two solar eclipses a year, and sometimes there are, not necessarily. Okay. As far as lunar eclipses, when the moon is behind Earth, also requires a node, but happens much more regularly because of its visibility, because we're able to see a lunar eclipse basically everywhere on Earth. Everyone's able to see a lunar eclipse because there's no path of totality. You just have to be on the surface of Earth to see it. Because in that case, the moon is passing through Earth's shadow. We'll say a little bit more about that in just a minute. Okay, we're gonna wrap this up so we can finish. Hopefully, get through the rest of the slides, but we're doing good in terms of the concepts at least. So close that. And I don't know what window it's sharing right now. Maybe nothing. Go back to that. There we go. Good, good, good. Okay, so then continuing on with our slides where we left off. Okay, so we saw the geometry. This is just showing. So these would be points where the moon is not passing through a node. Okay, so here they're just showing that there's not, you know, even during a new moon, right? We don't the shadow is not hitting Earth. So the line of sight, see the line of sight from Earth, we see the moon, sure, but we don't see its shadow. That's what this dashed line is showing. Is that yeah, sure, the new moon is perfectly visible, and this angle is dramatized, right? Because really it's only 5 degrees. But point being is that we can't see the shadow. The shadow misses Earth. Okay, so that's the solar eclipse. The lunar eclipse, I just want to quickly summarize. It's created at the exact opposite phase. Lunar eclipses only occur during full moons, whereas, of course, solar eclipses only occur during new moons. Because in order to have a lunar eclipse, the moon has to pass through Earth's shadow. Right? So here's the geometry for a lunar eclipse. Here is Earth. Right? Well, here's Earth. Here's its shadow, just like every astronomical shadow, it narrows down like a cone. So in order to get a full lunar eclipse, the moon has to pass through our umbra, our total shadow. And that's when we have the moon completely not illuminated by sunlight. And the total lunar eclipse are the ones where the moon becomes red. Because once the moon is completely in our shadow and it's not receiving any sunlight directly, it only receives the refracted light from our atmosphere, which is all bent into the red spectrum. Something we'll talk about more in chapter 5, how light can change color when it bends. And that's the sunset. So then what you see during a total lunar eclipse, where the moon appears to be red, a little bit dimmer as well, is it reflecting the whole all of Earth's sunsets and sunrises, for that matter, around the whole edge of the planet, because that's the light that is actually making it to the moon and reflecting back towards the side of the Earth that is at night and able to see it. Okay, so that's what a lunar eclipse is, a total lunar eclipse. Okay, and then I already gave it away, so I'll tell you, it's that dull coppery red color because of the red light of sunrises and sunsets. Okay. Here's what it looks like, and this illustrates a neat idea, is that so we see just a full moon initially, and it just goes in order from left to right, starting in the upper corner. So this is before the moon has passed into Earth's shadow. Okay, so this would be during a time where you have the right conditions for a lunar eclipse. Then the moon starts to pass through Earth's shadow, as shown here, and it starts to get covered. And covered, by the way, by a clearly curved surface, which is historically and also contemporarily one of the good arguments for saying that Earth is a circular body. Obviously, these days it would just be a rebuttal for a flat earther. And historically, it was one of the ways that early philosophers began to realize that Earth had to be a sphere was because of, well, lunar eclipses, right, which are regularly observed. Okay, but we see that circular shadow from Earth covering up the moon, no color change yet. That's because even when there's still just a sliver of the moon, this light is so much more intense because this is the light that's coming directly from the sun and getting reflected off the surface of the moon. It completely washes out any red light that would otherwise be visible. It's only once the Earth completely is blocking the sunlight that we're able to see the red color of our reflected sunsets and sunrises being reflected off the moon back to our eyes. But then as soon as it starts to leave the shadow, the color fades back to white. You can see. All right. Yep. This is talking about the atmosphere and where the color comes from. So the light during a lunar eclipse comes in. The atmosphere is shown not to scale here, because here the atmosphere looks like it's maybe a quarter of Earth's radius. As I mentioned before, the value from the center of Earth to the surface is 6,700 kilometers. So we could roughly round to 7,000 kilometers. This value generously is 150 kilometers. So we're talking about, something that is a, 650 times thinner. The atmosphere is 50 times thinner, and that's again being generous than the radius of the planet. So, if this was actually drawn to scale, well, if I wanted something 50 times shorter than the longer red arrow, you'd imagine it would just be like a tiny, tiny blue, border around the green Earth. But anyway, here they're showing it to be more dramatic and thick, so they can clearly show the light refracting through it. Okay, so when the light passes through any transparent medium, in this case, the atmosphere, composed mostly of nitrogen, but also, as we well know and appreciate as living beings, oxygen and some CO2. Well, it gets bent because of the different chemical compositions bend light differently, and it also separates the light. And what happens is the red light bends the least, and that's true of any transparent material, maybe some rare exceptions, but true of water, diamond, most transparent materials for visible light at least, bend red light the least. And so that means that it's the light that's going to pass through the most. That's why when you see the sun, when it's really near the horizon during rise and set, you only see the red because all the other light isn't making it to your eyes. So often, as a general advice, the way I found over the years to always make sure I'm thinking about light the right way is always just think about what is making it to me. What light is reaching my eyes. As long as you keep that as your baseline understanding, you can work out a lot of ideas. And that's what happens with, the idea of refraction and why sunsets are red, right? But then that light is the very light that gets bent, makes its way to the moon, which otherwise would be, I guess, in total shadow, except for maybe some light that we create as human civilizations, light, but that'd be much dimmer. But by far, the light that is getting reflected off is all that red light. So the reflected light is the refracted light, which are kind of funny because they're such similar words, right? So refraction leads to reflection, and that leads to a red moon when it's in our shadow. There you go. All right, how we're doing on time? Good. All right, so now we will move right on to our next topic and briefly talk about tides. Appropriately, as we've been talking about for a while, tides have to do with the moon. Talked about phases of the moon, eclipses, which involve the moon one way or another, and now tides. All right, so if we think of gravity, at what point on Earth is the gravitational force from the moon the largest? Point A, B, C, or D? Think about what you know about gravity. Okay, we got one vote for A. Yeah, okay. Bunch of votes for A. Think you're all right? Yes. Pretty straightforward, right? Because it's closest. Okay, so there you go. Stronger gravity at point A because you're a little bit closer. As I said before, it's not a big difference, but it's measurable difference. Okay. After all, the moon is 60 times further, right? So this from C to A, that distance, well, if you multiplied it by 60, you would get the distance to the moon. Okay. And it's funny, the moon is actually shown to be a little bit too small here. It's just rarely done. Its distance is definitely not accurate, nor is it meant to be accurate. Okay. And the meaning, there we go. Okay. So then that means that we have a difference in the gravitational force. So the variation in the gravitational force on one side of the planet versus the other side is significantly, not dramatically, but significantly different. Okay. And it's fair to say that's because of the large size of our moon. The moon is big. When we talk about the solar system as a whole and kind of general trends in the solar system, I'll remind you about that it really is unusual for a terrestrial planet, as far as we know, to have such a big moon. Right? So we have a big moon, and so then we have a pretty strong gravitational pull from that moon, and then it's different on the two sides of the planet. Okay. And that's what sets the gravitational tug from the moon apart from the gravitational tug from the sun. Because the gravitational tug from the sun is actually stronger. Strictly speaking, it's just stronger, but it doesn't change much between the two sides of the planet. And that's why the sun doesn't really do much for tides. It contributes to them a little bit, but it's the fact that the moon pulls so differently on the two sides that creates the sloshing that we know as tides. Okay? So we end up having two tides a day. There is a tide, two high tides a day in particular, right? But also two low. There's a high tide on the side of the Earth that is closest to the moon, and a high tide on the side that's furthest. Okay. A lot of people will guess the first one, high tide on the side that's closest, because they think, oh, okay, the water's getting pulled towards the moon. Okay. But then why would there be a high tide on the other side as well? Well, that's because it's not really about the water getting pulled towards, and this is just showing it. Right? Here's the Earth spinning. So we spin through the tides, so to speak. Okay. Obviously, these tides are really not to scale because although there are atmospheric tides, by the way, the atmosphere also experiences tides. Atmosphere gets thicker and thinner and matters for satellites. But what we care about is the ocean tides. Okay, being dwellers mostly on the surface and not in orbit. So think of these as oceans, right? But really thick oceans. And so the Earth like spins through these tides, so to speak. Okay? So that's what we're showing here. Okay? And now let's briefly talk about the influence of the sun, and I'll come back to my comment about why people often, think that it's strange that there's a high tide on the far side from the moon. So when the influence of the sun and the moon are aligned, that creates a stronger tide. Those are called spring tides. So they're just a little bit stronger than they would be otherwise. And okay, spring tides, when they're not aligned, then we have neap tides, which are a little bit weaker than they would be otherwise. And it's neap being NEAP, right? So spring tides, sun's gravitational force increases size of tides. What is the phase of the moon during spring tides? Which only one of these, there's more than one phase that is possible, but of the options, only one of them is correct. Yep, absolutely. Feel free to leave early. I'll be posting this recording so you can see the last little bit that you missed. Thank you for asking. Yep, the new. In order to get spring tides, you have to have that alignment. Very good. Okay, so the new moon, the full moon can also lead to spring tides. So both full and new moons lead to spring tides. Right? So here's the not aligned one. So you can see, right, the moon dominates tidal effects, but when the sun is acting perpendicular, it's basically making the low tides less low and it's making the high tides less high. And that leads to neap tides. All right, I'm going to just show you the answer to this one. Neap tides can occur during the first quarter. I say that because it has to be exactly perpendicular. And this phase, as I'm sure you're able to work out by now, being experts on lunar phases, is a quarter moon, first quarter. Could also be a third quarter, but that was not an option. All right. So what I'll briefly say, because it can get pretty complicated, but the reason that we have the two tides, and I'll go back to a good figure to show that, is because it's not just about pull. And I'll sort of argue it as being that if it was just about stronger pull, if a high tide just occurred because that side of the Earth was closer, then there would just be a high tide on just one a day. So instead, think of the two tides as being causing the movement of water to build up because you have like of these the oceans are this huge dynamic system, right? And when they're getting pulled directly either away from the surface or towards the surface, so away from the surface in the case of the side facing the moon, or towards the surface, so straight down in the case of the side facing away, that causes the movement of water to be less effective than otherwise. So it's like causes a buildup, a sluggishness of the water. And that is an overall structure of the ocean leads the tides. And to sort of drive that point home, think about how variable tides are, if you've heard. Different locations have very different tidal effects. Some coastlines have really high, really dramatic tides, whereas others don't. So, and that's all down to the geometry, what part of you know, what currents you're able to get. So then if you say, okay, well, let's ignore all that and just look at the open ocean, well, that's where you can make a generalization about the ability of the water to move through the open ocean is being impeded, right? Slowed down at these two relative locations to the moon. So that's why there's two high tides, one on the far side and one on the near side, relative to the moon. Last little bit here, and I'll just try to quickly get through it. It's been so much content. I'd love to finish 5 minutes early. And this is just talking about, as I hinted at before, and I said we'd get back to, that's the difference between these different types of measuring time. Okay, that's the topic of this section. Okay, so cycles in the sky influence our human experience. Great. Okay, so in the full orbit of Earth around the sun, well, if it took 360 days and the orbit of the moon around Earth took exactly 36 days, how many months would there be in the year? Well, I think you can do the math. Exactly 10. And that'd be a nice clean result, right? Now, in this case, it'd have to be, the phases rather than the orbit of the moon. So already there's a little bit of, detail to consider. But if that was the case, if a full phase cycle took exactly 36 days and our orbit took exactly 360, then we'd have a really clear division between months and years. But it doesn't, right? Instead, we end up with, and this would be another clean number, but instead we have an orbit that takes 365.2422. which we actually tend to round to 365.25, which is interesting because it should round down, but we like to make it a quarter. Okay, so this is our orbital period, okay, around the sun. And then the moon's phase cycle is 29.53. Now, I take a little bit of umbrage with this slide because they say orbit. That is wrong. It's phase cycle. All right. And the textbook does mention the difference briefly. And so, but this accounts for, the moon getting back to its orientation between the Earth and the sun. So 29.53 days is the time it takes for a full to go from new moon to new moon. So a full cycle of phases. Again, that's almost 2 days longer than the time for it to actually orbit around us, which is often described as orbit relative to distant fixed stars. Okay. Now, to directly tie in with that, and kind of interestingly, that the slides do get into this difference, but not the difference with the month. So that's why I wanted to mention both, is that if we consider that same idea, the same idea that I've been purporting for the difference between the month that's the orbit, the synodic month, and the solar month, which is the phases, well, let's do it for the day. For the day, we have the sidereal day. And the sidereal day is the time it takes Earth to complete a full rotation. So that would be if you're on the surface of Earth and you're pointing to a constellation, you would come back around after a sidereal day and you'd be facing that same constellation because it's a distant star. And that's some relative fixed point. But in the time that Earth has completed that full rotation, Earth has also moved a little bit around the sun. Not as much as happened during a whole month, but about 1/365th, right? So a fraction, but still a fraction. And that's showing right here. See, Earth day one, there you are. You're that really tall person. You rotate all the way back around. Okay. Well, once you rotate all the way back around, a full rotation, you're not facing the sun anymore because the Earth has moved a little bit in its orbit. So you have to turn and, your perspective on Earth to turn an extra 1 degree in order to face the sun. And where did the 1 degree come from? Well, it came from an approximation of saying, well, shoot, there's 360 degrees in a circle. There's about 360 days in a year. No coincidence there. And, that's why we're approximating it as a degree. Obviously, an approximation because 360 does not, in fact, equal 365.2422, right? But close enough. So if we just approximate it as 1 degree, that's the extra turn you need to actually get back to the sun being in the same position at the same time. And that's what we think of as a day. Okay. So when we talk about days, we are actually talking about solar days. That's considered a day. And most importantly, it's exactly 24 hours by definition. Okay. So a solar day is exactly 24 hours. A sidereal day is not, and it's shorter. Because think about it. The sidereal day, you you got back to where you started relative to some, distant point, remote celestial, object, and you had to turn an extra amount to get a solar day. So obviously the solar day is the longer one. Okay. And we'll skip this, and this, yeah, that's fine. But the difference between them, okay, so the solar day is exactly 24 hours, and that again is our baseline. But the sidereal day is 6 minutes shorter. Okay. But everything that we use for time, our time zones and everything are based off of the solar day. And when we talk about there being 365.2422, that's also measured in solar days. So that has been chosen as the standard, but it was a choice. But it was one that scientists made, and it's got to stick with it and base the whole system off of it. Okay, so there we go. That is our whole chapter about a bunch of motions and orientations, and a little bit about gravity when we talked about tides. So thanks for sticking it out, And be on the lookout for that quiz, our first Canvas-based quiz, unless you're one of the students that did a makeup, because you added late. But we'll have more of these in the future, and I'll be curious how it goes. And we'll still do both because I still want to have the Zoom ones to encourage attendance. But I'm going to stop the recording and wrap things up.